In a high-energy collision, an electron and a photon do not simply bounce off one another. Their interaction is governed by a precise mathematical exchange. This exchange is dictated by the Standard Model, specifically the U1 gauge symmetry that oversees the electromagnetic force. This specific branch of the model defines the behavior of a single variable, lowercase e, the elementary charge. Classical physics treats charge as an inherent property, a static label fixed to a particle like mass. However, modern theoretical physics approaches charge as a dynamic result of internal mathematical symmetries. Determining which of these views is correct is essential to understanding the early universe. It forces us to ask if charge is an accidental byproduct of the Big Bang or a rigid geometric requirement built into the vacuum itself. The path to answering that question begins with Nother, who identified a profound link between mathematics and physical reality. Nother's theorem establishes that every continuous symmetry in a physical system leads directly to a conserved quantity, a value that the universe refuses to lose. This complex plane visualizes a quantum wave function. These rotating vectors are probability amplitudes, representing the likelihood of a particle's state. If we rotate every arrow on this plane by the exact same angle at once, the physical outcomes remain identical. This is a global phase shift. Because the physics is invariant under this global rotation, Nother's theorem dictates that a specific quantity must be conserved, electric charge. But the universe allows for even greater complexity. If we attempt a local phase shift, rotating arrows at different rates depending on where they are in spacetime, the symmetry is destroyed. This local variation introduces an anomaly into the Dirac equation. The standard derivative no longer works, as the changing phase creates a mathematical mismatch. To restore the symmetry, theorists must introduce a correction, the covariant derivative, or d mu. This new derivative requires the presence of an additional term, a mu, which corresponds exactly to the electromagnetic potential. The photon and the electromagnetic field it carries is not an optional feature of the universe. It is a mathematical necessity required to maintain local symmetry in the face of varying quantum phases. When we combine these symmetry rules, we get the quantum electrodynamics action. At the center is the interaction term. Here, the variable E dictates the strength of the relationship between the electron and the electromagnetic field. These variables describe the physical moment an electron emits or absorbs a photon. This is the vertex used to calculate the probability of Compton scattering, the deflection of light by matter. Richard Feynman and his contemporaries used these diagrams to predict the behavior of electrons with an accuracy exceeding 1 part in a billion. Within this framework, E acts as the coupling constant, the numerical bridge defining the scale of electric interaction. However, QED has a significant limitation. While it explains how charge behaves, the math works equally well for any value of E. Purely within QED, charge could be continuous, any fraction or decimal. The theory does not explain why every electron in the universe carries the exact same discrete integer charge. To find the reason for that quantization, we turn to Paul Dirac and his 1931 investigation into the geometry of the vacuum. Dirac hypothesized the existence of a magnetic monopole, a single point source emitting a massive magnetic field evenly in all directions into the vacuum. A monopole creates a topological process. Because the magnetic field lines diverge, the vector potential cannot be defined continuously over a sphere enclosing the source. It leaves a mathematical tear. If an electron orbits this monopole, its wave function must remain consistent. To resolve the tear in the field, the electron's total phase shift after one orbit must be an exact integer multiple of 2 pi. This requirement leads to the Dirac quantization condition. It forces electric charge into discrete units to remain compatible with the monopole's geometry. In modern terms, this is the geometry of differential cohomology, where the electromagnetic field is defined as a connection on a principal U1 bundle. If even one magnetic monopole exists, the global topology of the universe demands that all electric charge exist only in quantized integer steps. These geometric rules extend far beyond point particles. In string theory, the charges of higher dimensional objects are governed by these same topological constraints. Today, Theorists utilize topological K-theory and Chern classes to calculate the charges of d-branes, using the mathematical foundation Dirac established nearly a century ago. We can now see the complete sequence. Nother symmetry conserves the charge, the gauge field mediates its force, and topology dictates its value. This suggests that electric charge is the observable manifestation of a geometric requirement, a necessary resolution of the universe's internal symmetries and its topological structure.